Earth has a mass of 5.97 times 10 to the 24 kilograms, and the moon has a mass of 7.35 times 10 to the 22 kilograms. If the distance between the Earth and moon is 3.84 times 10 to the 8th meters, what is the gravitational force between the two? So before we really start doing this problem, let's briefly talk about what this situation entails. So as we know, gravitation, Newton's law of universal gravitation, we know that equation, Fg equals G m1 m2 over r squared, and we'll get to the equation in a second, but let's talk about what it means first. We can see that any two objects with mass m1 and m2 that are separated by a distance r, which is the radius, because again we're thinking circular motion here, is separated by a distance r, it has a gravitational attraction between the two, gravitational force. So if we look at our two masses here, so the Earth, literally the moon is getting pulled towards the Earth, so there is a gravitational force Fg on the moon by Earth, and the moon technically is also pulling on the Earth as well. So there's Fg acting on the Earth. Now, we talked about Newton's laws, action-reaction. It so happens, even though they're different masses, that these Fgs, these gravitational forces on the two, are equal to each other. But because the masses are different, the accelerations are different. But understand that there is gravitational forces acting on both, and that's what we're trying to solve for here, Fg. Now we have a constant in this problem, capital G. This is not G. This is not little g. This is not 9.8. This is a gravitational constant. It's on your equation sheet, 6.67 times 10 to the negative 11. So that's where we're going to plug in for G. So we go ahead and multiply all the values. So G, again, 6.67 times 10 to the negative 11. We have the mass of Earth, which we can see is right there. 5.97 times 10 to the 24. We got the mass of the moon, 7.35 times 10 to the 22. And then we divide it by the radius squared, or the distance between the two squared. Now be careful that that radius, when we think about math, when we think radius and diameter, we don't want to double that, because remember, the moon is traveling in a circular orbit around Earth. So really the distance is the radius of the circle. So 3.84 times 10 to the 8th, and we have to remember to square it because that is part of the equation. And when we go ahead and do all that, we get an answer of 1.98 times 10 to the 20th newtons. Now that is a very large number. You look at that exponent, positive 20, we talked about in the first week of school, that a positive exponent like that times 10 to the positive 20 is a huge number. But that's okay, that makes sense, because look, we're dealing with two planets essentially, two planetary objects, Earth and the moon. So that force is going to be very large. If we use this equation for smaller masses like myself or yourself or a textbook or anything that we can physically grab, that number would be a lot smaller, but it's kind of neat because this equation works for all objects. Now, in terms of plugging this into the calculator, you can write times 10 to the exponent 20, or remember, you can use that EE button. You could use that EE button. That EE button represents times 10 to the. So you would write EE and then the exponent, whatever it may be, and you should get an answer that is the same. As you're watching this video, just to make sure, I would pause this and make sure that you can actually get the correct answer by typing it in, because sometimes in this type of problem with these big of numbers, the easiest mistake to make is not plugging it into the calculator correctly.